Good afternoon, good morning, everyone. Thank you for joining and welcome all of you for the monthly webinar series of IEEE Sensors Council. So this is a webinar 8 on From Light to Insight, Lidar Camera for Methane Emission Monitoring. So it's good to have Dr. Manasi with us today. So before kick off the presentation. So we will have a few minutes of Q&A session at the end of the presentation. You can type your questions in the chat box anytime, so we can discuss those at the end of the presentation. And so this session is being recorded, and then we will upload into the IEEE Sensors Council website and also YouTube channel as well. If you miss the past webinars, you can go there, IEEE Sensors Council website, and then you can listen the past webinars. So before going to the technical presentation, I would like to introduce Dr. Manasi. So Manasi Doshi is a senior research scientist at the Schlumberger Doll Research Center in Cambridge, Massachusetts, USA. She received her PhD in mechanical engineering from the University of Texas at Austin in 2021. Her research spans sensors and algorithms development, computational molecular dynamics, and theoretical modeling of mixed quantum classical systems. She has extensive expertise in chemical sensing technologies, ranging from chemiresistive to spectroscopic methods, as well as nanomaterials design and characterization. So her work with the nanomaterials include developing functional surfaces and engineered nanostructures to enhance the sensing performance, sensitivity, and selectivity. So her work is driven by a strong interest in advancing technologies that support industrial decarbonization. So we are very fortunate to have Dr. Manasi with us today. Welcome, Manasi. And without any further ado, I pass it to Manasi. Please go ahead.
Yeah, thank you, Nagesh, for the kind introduction. So I'm Manasi Doshi. I am a senior research scientist at Schlumberger Doll Research Center in Cambridge, Massachusetts. So at SLB, formerly known as Schlumberger, we have developed a camera combining principles of laser absorption spectroscopy and Lidar to monitor methane emissions. In today's presentation, I will first spend some time discussing why methane monitoring is essential, then go through the camera technology and workflow and discuss results from a blind testing that we participated in. So methane is the second most important greenhouse gas after carbon dioxide. It plays a major role in global warming. As shown in the figure here, about 60% of methane emissions come from human activities, such as fossil fuel use, agriculture, waste handling, and biomass burning. The remaining 40% is from natural sources. Of the 1.2 degree global temperature rise so far, methane emissions are responsible for roughly half a degree. Also, methane is far more potent than carbon dioxide. Since different gases have different atmospheric lifetimes, we compare their global warming potential as a function of time. So over a 100-year period, methane is about 28 times stronger than CO2. But if we look at a shorter time frame, so 20 years, it's 80 times more powerful, which means that if we emit 1 kilogram of methane today, its global warming impact over the next 20 years will be equivalent to 80 kilograms of CO2. But this makes methane a prime target for short-term climate action. If we cut methane now, we see benefits quickly, and reducing methane emissions is one of the fastest ways to slow global warming in the near term. Oil and gas is the largest industrial source of methane emissions. Why? Because methane is the primary component of natural gas. So any leak across the oil and gas supply chain, whether during production, processing, or transport, is mostly methane emissions. In addition, venting and flaring, often done for safety or operational reasons, also contribute significantly to methane emissions from the oil and gas sector. Now, take a look at this chart from the International Energy Agency. Going from 2020 to 2030, we can reduce the overall intensity of emissions from global oil and gas operations by almost 50% if we mitigate methane leaks. That's the light purple bar between 2020 and 2030. So reducing methane emissions is an urgent priority to reduce the overall emissions of the oil and gas industry. But to mitigate methane emissions, we first need to understand where the emissions come from. For non-oil and gas sources, such as agriculture, the emissions are relatively stable over time, which often makes emissions tracking a mathematical problem. In contrast, emissions from oil and gas activities are highly variable. So here are plots from three academic papers showing how methane emissions arise from various stages of production. So that's the pie chart on the left. Then various geographic regions in center and various facility types on the right. And without going into the details, it is quite clear that emissions can occur at any stage of production, in any location, and from any facility type, and also at any emission rate. Additionally, the emissions are often intermittent, which means that they can start and stop and then start again at random times. And this variability makes emissions from oil and gas harder to detect and quantify, especially if we rely on very periodic measurements through satellites or drones. So, the most reliable way to accurately measure oil and gas methane emissions is through continuous monitoring. Continuous monitoring ensures that we capture both persistent and intermittent leaks as quickly as possible. So we developed a camera that we call the methane Lidar camera. It combines aspects of laser absorption spectroscopy and Lidar to continuously measure methane emissions. Laser absorption spectroscopy is a powerful technique for detecting and quantifying gases. The principle is straightforward. When a laser beam passes through a gas, certain wavelengths are absorbed by the gas molecules. By measuring this absorption, we can determine the gas concentration, usually by using the Beer-Lambert law, which relates absorption to the amount of gas along the laser's path. So, laser absorption spectroscopy is an extremely sensitive, real time, and selective measurement technique. Each gas has a characteristic absorption spectrum, which allows us to distinguish one gas from another if we choose the wavelength correctly. For methane, the shortwave infrared region is ideal, specifically around 1651 nanometers. As shown in this plot, the absorption here for methane in red is strong around this 1651 nanometer wavelength, and interference from other atmospheric gases such as water vapor is minimal. Now, to develop the hardware of our camera, we partnered with a UK-based startup called QLM. Our camera uses tunable diode laser absorption spectroscopy. The optics diagram is simplified here. The laser source is a commercially available distributed feedback laser with an eye-safe 10 milliwatt output. We use or our laser rapidly modulates its wavelength across the methane absorption line at 1651 nanometers to measure methane concentration. So instead of just measuring one single point, as shown in this plot, we continuously sweep the laser across the absorption line so that we can capture its shape and we can prevent albedo effects from the reflecting surface or atmospheric conditions. Now, going back to the figure on the right, the emitted laser beam reflects off a diffuse scattering surface and returns to the camera. The detection of the returning signal is handled by a Peltier-cooled single photon avalanche detector or SPAD. The SPAD can detect individual returning photons, so it is a very high accuracy methane concentration measurement. Simultaneously, a time correlated signal, very similar to a traditional LiDAR system, measures the distance traveled by the laser. And we use a single coaxial optical transmit and receive axis coupled by a polarizing beam splitter denoted by the PBS here. This setup maintains alignment over long ranges and protects the SPAD or our detector from direct reflections. Now, the laser beam measures the methane concentration and the LiDAR range along its very narrow path. To expand coverage, we pass the laser through a pair of Risley prisms. These prisms redirect the beam and allow us to scan across fields of view. The laser can move in circular patterns like the one shown here, or in spiral patterns to cover larger areas efficiently. The camera usually acquires data points at about 100 hertz, which enables very rapid measurements. Um, and although the field of view gets filled in by data points in about a minute, we usually scan into each individual field of view for about 2 to 4 minutes, uh, so that we can get better averaging and better signal to noise ratio. So within those couple of minutes or few minutes, we acquire several thousand data points, which contain complex information, including signal intensity, LiDAR range, and spectral information. So here is an image created from 4 minutes of data acquisition. I'll explain the image a little out of order, starting with the bottom left plot. So on the, or actually with the bottom right plot. So here you can see the bottom right plot is the LiDAR point cloud, which reveals the structural details and gives us the distance information. On the bottom left, we have an image of the basic intensity level of the return signal. And like almost like a normal camera, we can actually see what the structure looks like. Now, the image on the top left shows the measured methane concentration along the laser's path, expressed in parts per million meters. Here we can notice the elevated methane levels, indicating that there's an emission in this field of view. And now when we overlay these two left images, so the methane concentration plot over the intensity map, we get the plot on the top right where we can pinpoint the emission coming from the source in this image. And these combined images are game changers. They provide unambiguous visual information about emission sources. And this makes mitigation quite easy on a relative scale because you can go and fix exactly the component or the equipment that's leaking. So the technology gives us the ability to detect and quantify methane concentrations. But using it as a true measurement device requires much more than just the sensor. It needs to be a complete system, uh, including planning, calibration, scanning strategies, data processing, and interpretation. In other words, the camera is just a starting point, and the real value comes from the integrated workflow that turns raw data into actionable insights. So we start on the top by planning the camera placement to ensure maximum coverage. Next, we deploy the camera and define a scan plan uh, in a way that it includes the sources that we want to monitor for leaks. Once the system is set up, we acquire plume images and that capture the methane concentration and structural details. And from these images, we detect the emission, quantify it, and attribute emission to specific sources. Finally, we analyze and report the emissions data, provides actionable insights for emissions tracking and for mitigation. And this end-to-end process, from planning to reporting, makes the methane LiDAR camera really a powerful tool for emissions management. So currently, our methane LiDAR camera can detect emissions up to 200 meters, and we are optimizing laser parameters to extend that range even further. To maximize visibility, we install the camera on a tall mast, like the one shown in this image. So this one's about 15 meters high. Uh, Installing at a tall location serves two key purposes. The first is that it gives us a top-down view of the facility. So this allows us to see more equipment than we could from the ground, and equipment are not obstructed by other equipment. And second, by elevating the camera, the ground itself becomes a diffuse scattering surface so that the laser can reflect off and get back to the detector in the camera, which means we don't need any external reflectors and we don't need any setup to detect emissions. The camera is mounted on a pan-tilt stage. The pan-tilt stage can move up and down and in a circle all 360 degrees. So it allows us to survey a wide range from a single vantage point. So we can think of it as a CCTV system, but designed specifically to detect methane emissions. However, oil and gas facilities can be quite complex with hundreds of equipments sometimes. So where we place the camera determines how much of the site we actually see. And to solve this as well as to optimize it, we developed a camera placement optimization algorithm. Using a satellite image or a 3D model of the facility, we can identify the best location that maximizes coverage. So here we can see a color map where certain colors, for example, the purples indicate that those locations are not great for emissions monitoring for this facility, while the green locations show places where if we install the camera, we can see most of the facility. Um, and we can also, using the app, try and understand which sources will be visible from the camera and which will be obstructed by other equipment or maybe beyond the range of the camera. Now, as I said earlier, the pan-tilt stage on which the camera is installed allows the camera to scan in 360 degrees and also up and down. So essentially, it can scan a sphere around itself. But scanning such a sphere would not only take a really long time, maybe even days, but it's also quite unnecessary. Most fields of view would contain nothing of interest. We'll be looking at the sky or the ground. And it will also take us longer to scan any location of interest, or the time between scans will be longer, which will increase the probability of missing short duration emissions that can start and stop between consecutive scans of an equipment. So instead, after installing the camera, we do a 360-degree scan once and determine where the equipment of interest are located in the facility. After that 360-degree scan, we stitch together a few hundred frames that we get, where frames are fields of views, to create a panorama as the one we can see here in this figure. And we've also created an interactive app for this panorama image. So we can click anywhere on the image and choose the discrete locations that we want the camera to scan. Based on the locations we choose, the app automatically creates a scan plan and the camera can iterate through the scan plan. For this facility and this image, the circles show the chosen fields of views or frames. Um, so we can see that it's a very small fraction of the actual 360-degree panorama. The camera can also zoom in. So if we are trying to detect methane from equipment farther away from the camera, we can get comparable signal to noise ratio by zooming in as we would get for equipment closer to the camera. So after we get the scan plan, the camera just iterates through it. So it monitors one location, goes to the next location, and keeps going across the facility. And once it's done with the full scan, it goes back to location one. Um, so once the camera starts its scan plan or acquiring data for each field of view, we algorithmically check if there's an emission in the image or not. More often than not, the emissions are above the limits of detection of the camera, and the images appear like the one on the left here, where there's a clear plume. Like if we visually look at it, or if an algorithm looks for it, it can clearly tell that there's an emission in the image. But sometimes we get images that look like the one on the right, where either the image is noisy or there is an emission, a very small emission close to the camera's limits of detection. And it can get quite challenging visually or algorithmically to tell if the emission is real or if it's just noise. So to improve our detection accuracy, we trained a machine learning classification model on a data set containing thousands of images with and without plumes. And our ML model has already surpassed human accuracy. So there are images where when we visually look, we cannot tell if it's an emission or not, but the ML model can correctly identify what's happening. So far, I've discussed how methane concentrations and distance can be measured using spectroscopy and LiDAR. And while these measurements are very important, a more actionable metric is to understand the rate at which methane is being emitted. To estimate the emission rate, we use a simple flux-based methodology that combines data from the camera with data from an anemometer, which is a wind sensor that measures wind speed and direction. The key idea is that when methane is released into the atmosphere, it travels with wind. That means the velocity of the methane plume is approximately equal to the wind velocity. And by knowing the concentration of methane in the plume and the speed at which it's moving, we can calculate the emission rate without relying on complex models or assumptions. And now the next challenge is understanding which piece of equipment is leaking. Um, Visually, of course, we can often tell what's leaking, but we don't want to manually look for leak sources in hundreds of images every day. Uh, the easier option is to automate it. But automating isn't straightforward, especially because the camera's field of view can be quite large. It is an angular field of view, so the further we go out in distance, the larger the field of view becomes. Which also means that multiple pieces of equipment may appear in the same image, as shown in the bottom image here. So to address an automated emission source detection, we developed an attribution algorithm that identifies the most probable leak source based on how the magnitude of methane concentration changes within the image and using the LiDAR range. The algorithm uses ray tracing to analyze the camera's line of sight and provides a list of equipment that are most likely responsible for the leak. So all of this is for individual frames. So for each frame or each field of view, we scan for a few minutes. We can then go through the detection process of whether an emission exists in that image or not. And then if an emission exists, we quantify it and identify the emission source. So individual observations like these act as snapshots. They are valuable on their own, but are limited in scope. To truly understand the life cycle of a methane emission, we need to combine these snapshots into a more complete picture. For this, we developed a dashboard that aggregates individual observations into emission events. So every time we get a positive observation, which means that every time we detect an emission in a field of view, our cloud-based algorithms check whether an emission is already ongoing at that location or if we have previously detected an emission at that location. If we have, we append the new observation to the existing event. If we haven't seen or if we don't have an ongoing emission at that location, we create a new emission event. Over time, when our system receives a series of negative observations, meaning no methane is detected at the same location where we previously detected an emission, we can automatically close the event. And once an emission event is closed, we get a detailed summary of the event. So the start and stop time of the emission, how the emission rate evolved over time, and the total methane emitted during this emission event. By doing so, we can track emissions. We can also use this information to report our emissions to various regulatory bodies. And ultimately, it also allows faster mitigation. Facility operators can maybe also look for correlations between their operations and the emissions events to try and understand what may be causing their emissions. So the workflow I just described is in this flow chart on the left, and on the right is a snapshot of our dashboard. where you can see the map of a facility. On the right is an individual um, detection that we have, the location where we detected it, the rate at which we detected, the date and time when it was detected. And on the bottom is a time series plot of where each circle is an observation. And then I've just tried to show some emission events where we can see an emission started at a specific location, went on for a few hours, and then stopped. And then another emission started at a different location or at the same location and then stopped again. So before moving on, I just want to show a quick video of the workflow that I just described. So I hope you can see the video, but this is a rendering of a typical oil and gas facility showing equipment of various sizes and shapes. Um, the hexagons here are the output from the placement app that I described, showing possible installation locations, and the optimized location was then highlighted. Um, the camera is then installed at this best location at the top of a tall mast on a pan and tilt stage. Once we begin uh, or once the camera begins operating, it scans the facility for emissions. So this predetermined scan plan is looking for emissions at different equipment. And when it sees an emission, it creates that or it computes the emission rate and identifies the emission source, and all the observations are published on the dashboard. Here, this is an example of an emission event where we can see the start and end time, the total methane emitted, and other information. And we can also aggregate it on larger time scales. So emissions tracking for weeks or months or even for years, if you want to see how the emissions vary across seasons or across operations. Um, So to test this end-to-end workflow that we just saw, we participated in a single blind study at Colorado State University's Methane Emissions Technology Evaluation Center, better known as METEC. METEC is a unique facility designed to emulate the emissions behavior and wind transport characteristics of real upstream and midstream oil and gas operations. They've outfitted a wide range of equipment, so wellheads, tanks, separators, with controlled methane release points. In fact, there are over 500 possible release locations across the METEC facility. So the study was single blind, meaning we, the participants, had no prior knowledge of when an emission would occur, how long it would last, where it would happen, or at what rate. This setup, combined with Colorado's unpredictable weather from February to April, ranging from snow to heat waves, created a realistic but very challenging test environment. And then our system's performance is evaluated by Colorado State University across several metrics, including detection sensitivity. So, how reliably can we detect an emission? Quantification accuracy. So, how closely does our measured emission rate match the actual release rate? And localization accuracy. So, how accurately can we identify the leaking equipment? And this blind test in the study gave us a very rigorous and unbiased way to validate our workflow and our detection and quantification capabilities. Oh, here we go. So these are the results from our METEC test. I'll start with the top image. That's our detection plot, where on the x-axis we have the emission duration that ranged from 15 minutes to about 10 hours. And on the y-axis, we have the average emission rate, which ranged from a few grams per hour to about just over 7 kilograms an hour. The green points are the emissions that METEC carried out that we successfully detected, while the red crosses are the ones we did not detect. And it there's a clear correlation here. We detected everything that was above approximately 45 minutes in duration and above half a kilogram-ish in magnitude. Um, Below that, we detected some things but not others, and that's because of two reasons. So the first is for the emission rate. So the camera has a limit of detection that's just so sometimes if all the conditions are correct or conditions work out, we may detect it, and other times we may not. The other is the duration aspect. So as I mentioned earlier, we scan a location or an equipment, then we scan the next one and we do that, and then we come back to the first one. The time duration between two consecutive scans of any equipment depends on how many sources you have at the facility and how granular you want to get. So at METEC, that time was about or just over an hour. So if an emission is shorter than an hour, there is a possibility that it will start and stop between our scans. Usually, oil and gas emissions are uh, intermittent, but not as short as 15 minutes. But since METEC tests uh, in the harshest possible conditions, there were emissions that were too short and happened between two consecutive scans of our camera, and we did not detect them. But as long as the emission was about our detection threshold in terms of rate, or if it was when the camera was looking at the equipment, we detected it as shown by all the green points. Moving on to quantification, I want you to focus on the light blue solid line. That is the line for the camera, while the other lines are for the other participants uh, who were also present during the blind test. So for the quantification, we have the uncertainty on the y-axis and the relative error on the x-axis. And as we can see, the uncertainty quickly reduces, or more like if we look at a 90%, so if we look at a 90% point on the y-axis, so that would be a quantification accuracy of 90%, and we vertically draw a line from the blue curve to intersect the x-axis, it is very close to 3, which means that our quantification accuracy is that 90% of our emissions are quantified within a factor of 3 of the actual emission rate. To put things in perspective, it is significantly better than all the other participants, as shown in this plot, where quite a few participants never even reached the threshold that I just mentioned. On the right is the localization accuracy. So again, looking at the blue plot or at the light blue plot, most of our releases are detected within 4 meters of the emission source. And this is extremely important for mitigation measures. When you want to try and fix a leak, the closer you can get to the source, the easier it is to identify what's leaking. And as you can see in this plot, all of our localization was under about 5 meters and most under 4 meters, and significantly better than other technologies, just helping mitigation measures and pinpointing the emission source. So on a comparative basis, the camera was the top performer at the METEC test. So the quantification accuracy, the localization precision, and time to detection, which is another metric that METEC uses, the camera ranked first out of the 9 participants. And for sensitivity, we came second. This is again based on what I said previously, where we missed some short leaks when the camera was looking at other equipment and not the one that was emitting. So Colorado State University has published all these results, and they are available um, uh, in this publication. It's linked in the presentation. The results are anonymous. They identify equipment by an alphabet, and the camera is equipment or instrument B if anyone wants to take a look. So just want comparing the camera. So there are other camera-based technologies that can detect methane. And like those technologies, our camera also produces an image of the methane plume that helps with understanding where the emission is coming from. But unlike other cameras, our system offers several key advantages. The first is it doesn't just show that the methane is present, so it doesn't just detect the emission. It also calculates how much is being emitted, uh, which helps understand which emissions are larger or smaller, and it also helps prioritize mitigation measures. Second, our camera uses a laser-based system. So it provides active illumination, and the camera does not require any naturally occurring light, which means it can detect reliably at night, in snow or in rain or across most weather conditions. And our spectroscopy also does not require thermal contrast. So there are cameras that need the gas to be at a different temperature than the atmosphere around it for them to detect it. In our case, we don't need that temperature difference or the thermal contrast. So we can detect emissions in any location and in any weather condition. The third is we can do facility-wide measurements. So our limits of detection are as low as zero point 0.4 kilograms per hour at 200 meters distance. Um, in contrast, if we compare them to optical gas imaging cameras, which are quite frequently used for methane emissions monitoring, their sensitivity significantly drops with distance, which means someone has to uh, carry that camera and go really close to an emission source before they can detect leaks. While for us, we can install the camera at one location and then scan the facility from that location without manual intervention. And that's the fourth point. The system is fully automated. So the detection, quantification, leak source, identification, everything is done automatically through algorithms, and we don't need manual operation or manual interpretation. And this is extremely important for scalability and wide-scale deployment. So in conclusion, uh, I just described a laser spectroscopy and LiDAR based camera system that can accurately detect, quantify, and localize methane emissions. The individual measurements from the camera can be aggregated on our dashboard that can then be used for tracking and reporting. So even facility operators can not only understand how their emissions vary over time, but they can also potentially track uh, how efficient their mitigation measures are, and if they have a reduction in their emissions because of this mitigation measure. They and then for the METEC single blind testing, we are best in, or the camera had best in class performance. And the last point that I didn't go through in detail in this talk is that the camera surpasses the regulatory requirements set and thresholds set by the EPA. Most places in the world have regulatory requirements to track emissions from facilities, and there are also often fines associated with excessive emissions in order to reduce climate impact. In the US, the regulations are driven by the US Environmental Protection Agency, or the US EPA. The US EPA also certifies measurement technologies based on a very rigorous evaluation process where EPA considers everything based from the fundamental physics of the technology that we discussed today to the actual performance at real facilities. And then, based on their evaluation, the EPA then approves technologies to be used for regulatory emissions monitoring for certain specific categories. So, the EPA can approve a technology for specific geographic locations, for specific limits of detection, or for specific spatial resolution. And earlier this year, our camera was approved by the EPA for all of its categories, which means that it can be used for regulatory methane emissions reporting from any oil and gas facility, irrespective of the facility location or their emissions profile. So that's it for the presentation. I'm happy to take any questions, and if anyone wants more information or has any other questions, feel free to reach out via email.
Yeah, it was great. Yeah, thank you, Manasi. It was great presentation. I really like the dashboard and then sensor placement optimization, fully automated. Yes, the results are pretty interesting. If anyone have questions, please type in the chat box or feel free to unmute yourself. Yeah, before they are thinking, I have a very quick question while they're thinking. So yeah, you mentioned the your LiDAR camera is like a better performance than the EPA threshold levels. I'm wondering how much the sensitivity levels it can ppm or it can do ppb levels.
Um, so the technology, because we measure the methane concentration along the laser path, it already has one length scale in it. So our measurements are in parts per million times meter. Um, so if we have, so if say we measure 100 ppm meter, it's that along the laser's path, it's 100 ppm times 1 meter length, for example. Um, the limits of detection by the EPA and by us are defined usually in emission rates. And for us, like I mentioned, it's zero point 0.4 kilograms per hour or slightly under it. So that would be ppm level concentrations, not ppb.
Yeah, yeah. Yeah, I'm just wondering, there's different technology like TDLS and then CRDS. Yeah, the different technology. Maybe can you highlight the advantage LiDAR camera compared to with those technologies like TDLS, CRDS, yeah, those type of sensors. Yeah.
So this is, in a way, a TD-LAS system. We
Mm.
do have tunable diode laser absorption spectroscopy. One of the advantages I would say over cavity ring would be everything's internal. We don't need mirrors. We don't need any internal reflections. So I think the advantages are mainly just the traditional advantages of TD-LAS over the other systems.
Yeah, I don't see any questions from the chat box, but yeah, if you would like to have questions later, yeah, so Mansi, she provided contact details, so you can feel free to reach out to her. And also, this session is like a on demand on YouTube or live. Some people are watching there, so that's why we see less people here. Yeah. Anyway, yeah. Thank you very much, Dr. Manasi. Appreciate sharing your thoughts on the LiDAR camera. This is a really important topic. Thank you very much.
Thank you so much.
Thank you. Yeah. Have a great weekend all.